This video is going to be on calculations of different parts of a titration. Okay, so I'm actually going to open up a new flip chart, and I'm going to flip back and forth between them. Got new flip chart. There we go. I'm going to draw some stuff on here. All right. So in this problem, like I said, I'm going to flip back and forth. I apologize for the jumping around. We are going to be titrating. We're going to be adding 0.200 molar NaOH to 24 milliliters of 0.350 molar HOCl. Let's classify those substances. What is NaOH? That is a strong base. What is HOCl? A weak acid. All right. Is there anything else that you think needs to be given for us to do this problem? No. No. Maybe like a constant we need? We need the Ka of HOCl. Ka of HOCl is 3.5 times 10 to the negative 8. Okay? All right. So we're going to be, let me flip over to the other flip chart now. All right, so we have a titration, and we're going to be like looking at the way the curve looks, the graph of that. All right, so if we are adding, actually let me draw my little, here's my beaker. Isn't it so pretty? Yeah, here's my beaker. Okay, inside this beaker initially is just HOCl. And then being added to that, here's my very well-drawn burette. Okay, very well drawn. It's a minimalist burette. Okay, so very well-drawn burette. Inside that burette is what? The sodium hydroxide. What concentration was that sodium hydroxide? 0.2 molar. Okay. Hey, what was the concentration of HOCl? 0.350 molar. And what volume of that did I have? 24 milliliters. Okay, great. And then we'll be adding NaOH as we go. Like, so the volume of NaOH is going to change. It's going to increase as we add more of it, right? Okay, so if we're going to be, and there is a pH probe. There's my pH probe. Yes, doesn't it look so beautiful? Yeah, has a little readout with numbers. Okay. You know, exactly accurate pH probe right there. Okay, but we're measuring the pH. So if we're measuring the pH, that's our y-axis. What's our x? Yep, the volume of NaOH added. Because that's what we are controlling, and we're measuring the pH as a result of that. Okay? Alrighty. So, before we've added any NaOH, before we've added any sodium hydroxide to this HOCl, describe for me, you know, the relative pH of the HOCl. It should be less than 7, right? It should be fairly low, you know, relatively. So it'll be, you know, we're not assigning numbers to this yet, but, you know, the starting pH at 0 is going to be, you know, we'll say it's that line right there. We'll write the number down once we calculate it. Okay? So let's actually go back to this and calculate that. So we're going to calculate the pH before addition of any NaOH. Before we add any sodium hydroxide, what's the pH of this HOCl? So HOCl is what type of acid? A weak acid. So how do we find the pH of a weak acid? A rice table. So our reaction is going to be our weak acid reacting with what? Water. And remember, always for Rice tables, it's an equilibrium arrow. What are our products there? H3O plus and OCl minus. We don't care about the amount of water. All right. Initially, how much H3O plus and OCl minus do we have? 0 and 0. And how much HOCl? 0.350. So my change is going to be minus x plus x plus x, 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 0.350 minus x. Cool? All right, what do I do next? Set up the equilibrium expression. So Ka equals concentration of H3O plus times OCl minus over HOCl. What? Can you focus, please?
No, I literally cannot.
What do I do next? Yep, plug in the values. So 3.5 times 10 to the negative 8 equals x squared over 0.350 minus x. So wait, is this minus x negligible? How do you figure that out? Initial over Ka, if that's greater than 400, it is negligible. Hey guys, you need to stop talking. And honestly, when the Ka exponent is smaller than like negative 4, which it is here, that minus x is going to be negligible. Okay? Since Ka is fairly small, that's going to end up being negligible. It makes our x value really small. Therefore, it's significantly less than the initial concentration, so the initial concentration is not going to really change when we get to equilibrium of our HOCl. All right, so now we just solve for x. What do you get? 1.11 times 10 to the negative 4, right? And that equals what? That's our H3O plus concentration. And then to find pH, we do negative log of that. And you should get what? .956. So fairly low pH to start. So on our graph here, this initial pH is 3.956, right? Okay. So now we're going to start adding our strong base. When we add strong base to something that contains a weak substance, what type of problem is that? It's an invader problem. Titrations are just a bunch of invader problems. Okay, because you're invading this weak substance with a strong base. An invader problem does not have to be a buffer being invaded by a strong substance. It can be just a weak substance being invaded by a strong substance. Okay, it's anything. That's any strong substance added to something else, that's an invader problem. Okay, so now we're going to add 5 milliliters of that sodium hydroxide. Okay, so when we set up invader problems, we write the reaction between the invading species, so OH minus, and the component it's invading. When it's invading a buffer, only one of those components will neutralize the base. Here we only have one component, and that's the HOCl. And that's going to be a strong arrow, a single arrow. Because remember, whenever you have a strong substance, strong acid or strong base, as a reactant, that drives the reaction to the right. It drives it to completion. There's no equilibrium associated with this equation. Okay? What are my products? Water and OCl minus. I like putting water on as the second product so then it's out of the way because you know we're going to cross it out anyway. All right. So now I need to worry about the amounts of these things and do the stoichiometry with it. Because when it's a complete conversion, when it's a strong reaction like this, one that drives to the right, it's just straight stoichiometry. There's no equilibrium, Rice table, or anything like that. What values, what units do I put on those values? Moles. I have to use moles for stoichiometry. Okay? So I have to calculate the moles of each of these things. So, do I know the volume of each of these substances? Well, initially I have none of this. We can just go ahead and put a 0 for the OCl minus. I need to know the volume and concentration for both the hydroxide and the hypochlorous acid, HOCl. I need to know the volume and concentration for each of those. Do I know the volume and concentration for each? Yes. We have 5 milliliters of OH minus, and it's 0.2 molar. We have 24 milliliters of HOCl, and it's 0.35 molar. So we need to calculate the moles of each one. 5 milliliters is the same as 0.005 liters. Times 0.2 is 0.001 moles. And normally I don't put units in tables like this. I'm doing it for this first one. Exactly. NA is a spectator because it's not actually affecting the outcome of this problem. It's just there along for the ride. HOCl, we have 24 milliliters. That's 0.024 liters. And it's a 0.350 molar solution, so that's 0.0084 moles. All right, which one of these substances is my limiting reactant? The OH minus. So all of the OH minus is going to be neutralized by the weak acid, okay? And it's a 1-to-1 ratio, stoichiometrically. So all of this goes away. That same amount of HOCl goes away, and then all that HOCl that's being neutralized, or that's being reacted, gets converted into OCl minus. So how many moles of HOCl are left over? 0.0074. All right. So now, at this point, what substances do I have left over? The weak acid and its conjugate base. So is this a buffer? Yes, which means it's scenario number 4. Good job. You did that all on your own. It's scenario number 4. We have a buffer left over. So when it's scenario number 4, what equation do you use to find the pH? Henderson-Hasselbalch. Okay, now, technically, what are you supposed to do with these moles? Convert them back to concentration. What if you forget to do that and you're using Henderson-Hasselbalch? Does it change anything? No, because the ratio is staying the same. However, if you forget to convert it back and it's any other scenario, you're going to get something wrong. So might as well get in the habit of just always converting back to concentration before finding pH. Okay? So we're going to divide both of these by the total volume that's in that beaker. In this beaker now, so we had 24 milliliters of HOCl to begin with. We just added 5 milliliters of our base. So what volume do I have now? 29 milliliters, or 0.029 liters. So divide both of those by 0.029, and then we're ready to plug this into our Henderson-Hasselbalch equation. So pH equals pKa plus log of the concentration of OCl minus over HOCl. And that will give us our pH. So right now you're dividing the moles by the volume to find the concentrations. We're going to do one other calculation before we can plug into this formula. What calculation is that? Defining the pKa. So do negative log of the Ka, and we'll get the pKa. I'm just going to write it down up here. What do you get as the pKa? Yep, you should get 7.46. So pH equals 7.46 plus log of, what do you get as the concentration of our conjugate base? 345? Okay. We'll do 3 sig figs. That's fine. I really only care about sig figs of the final answer. All right, and then HOCl, 0.255. Cool. What do you get? Well, technically we should have only had 2 sig figs for these concentrations because of the volume. But again, as long as you remember that you need to round to 2 sig figs when you find your final answer, just round it there. So 6.59. Okay. So look at that. Just the addition of 5 milliliters of sodium hydroxide, our pH increased from almost 4 to 6.5. That's a pretty substantial increase. Okay. So our graph is going to shoot up. What was that number? 6.59? Yeah. Okay. So now my pH has shot up. But we're not going to do these calculations, but what actually ends up happening is the pH kind of tapers out for a little bit. It tapers for a little bit because once you start adding sodium hydroxide, to this weak acid, the products are always a buffer. We always have a buffer being made. Okay, so the pH isn't going to change that much here. It's going to kind of stay consistent. It's going to increase, but not as dramatically as when we first started adding the base. This is actually called the buffering region. I'll label that in a moment. And then once we use up all of the weak acid, the pH shoots up, and then it's going to level back off again. Okay? So this right here, this is called the buffering region. Okay, it's the buffering region. Within that, we have a buffer, right? So the pH, like I said, it's not changing too much. Calculations during this part will always be scenario 4. Because you'll always have a buffer there, so you always do Henderson-Hasselbalch. What is this? I'm going to change colors. What is this part, that point called? The equivalence point or the end point, you know, all these different terms. That's the end point. Does anyone remember what scenario happens at the end point? Scenario 3. Everyone's favorite. And yes, we will be doing that today. So that's scenario number 3. Do you remember maybe from last year, and I'm not making a joke here, I mean like when you took first year chemistry. Does anyone remember what is special about the equivalence point? And I think we've gone over it already this year, though you might not remember. Does anyone remember what's special about the equivalence point? What's equivalent at the equivalence point? mean, it's not specific enough. Nope, not the weak acid and weak base. Weak acid and strong base. So your two reactants in this titration. And we're actually not going to talk about concentration. We're going to talk about moles. So at the endpoint, the moles of our weak acid will equal, and more specifically, I'll put HOCl, will equal the moles of OH minus. Okay? So moles of HOCl equal moles of OH minus. Because they're equivalent. There's a complete neutralization. And then beyond the endpoint, it's going to actually be scenario 1. And we'll do one of those if we have time today. Otherwise, we'll pick up with that later. Okay? My goal is to get to that today, though. All right? We're going to come back to this graph in just a little bit. We're going to add in more numbers as we go. Let's go back to our calculations. Nope, sorry. One more thing I want to talk about here. Within the buffering region, so let's go back to the buffering region. Okay? Within the buffering region, there's a point halfway along that is called the halfway point. Okay? Or the halfway to equivalence point. A very special circumstance occurs at the halfway to equivalence point. And that is the concentration of the weak acid equals the concentration of the conjugate base. So different from the neutralization point or the equivalence point. Yeah, you had mentioned that earlier, and I was like, nope, not there yet. Okay, so the halfway to equivalence point, the weak acid and the conjugate base are in equal quantities. So I actually, I changed C and D from in your packet to these two problems. So take a moment, and I'll pause it while you do this. Take a moment to correct those two problems, and then we'll finish going over them. So at the halfway to equivalence point, since the conjugate acid, or sorry, the weak acid and its conjugate base are equal, remember, pH equals pKa plus log of the conjugate base over the weak acid. When these two concentrations are equal, what happens to this term? It becomes 0. So therefore, pH equals pKa. At the halfway point, pH equals pKa. You, hopefully, supposedly, theoretically, in the last lab we did, that's what you were doing. That's why you were able to use the pH to find the pKa, because you had equal concentrations of your weak acid and its conjugate. Okay? So pH equals pKa. So for this problem, the pH at the halfway to equivalence point would be what? Okay, we've already calculated it, so it's 7.46. Bless you. Okay, so back on our graph, I'll come back to that slide if you're not done with it yet. At the halfway point, again, this is not really to scale, but that'd be like 7.46 right there, that halfway point. I don't think it's going to have a little bit more of a slope, and I just didn't represent that. It's not to scale. Not to scale. Not to scale. Okay? So, the halfway equivalence point, we have a pH of 7.46. Now, let's calculate the volume of sodium hydroxide we need to reach that halfway point. Okay? So, in our reaction, we have hydroxide reacting with HOCl, and that's forming OCl minus plus H3O plus, or sorry, H2O. H2O. Okay. We have a finite amount of which substance? HOCl. Because we can always add more OH minus, right? Like we have a fixed amount of HOCl. Because it was what we put in the flask, or in the beaker, and that's it. And how many moles was that? 0.0084 originally. Originally, we had 0.0084 moles of that. We don't care about water. We originally had none of the OCl minus. We need to add enough OH minus so that we end up with equal amounts of HOCl and OCl minus. So how much of this needs to be neutralized? Half of it. So we need to add enough of this to neutralize half. So how much of the OH minus, how many moles do we need to add? 0.0042 moles. So that's all we really need to finish out problem D. We don't need to finish out the chart. Okay, so all we need to know is we need to know that we need 0.0042 moles of OH minus. What else do we know about hydroxide? Well, its concentration is 0.2. Find the volume. Because we know concentration is moles per liter. So if we know the moles, we know the concentration, we can find the liters. And what do you get? 0.021 liters of NaOH needed. So 21 milliliters, right? So back on our graph, this point here would be 21 milliliters. All right, now that's the halfway to equivalence point. The equivalence point, what volume of NaOH would we need? 42. Because it took us 21 milliliters to get halfway there, it would take 42 to get all the way there. Now, let's go through the math though. What if problem E, which is on the next page for me, I'm giving you guys just a couple more seconds with this slide. What if we hadn't done the halfway to equivalence point volume? What if finding the volume at the equivalence point was its own problem in itself? How would you go about doing that? Well, we know that the reaction is OH minus plus HOCl forms OCl minus plus H2O. Again, we don't care about water. All of these titration problems, always think back to like clean slate. Like it's a problem from the beginning. The previous steps did not occur. It's like a problem all on its own. It's not a continuation of the earlier problem. Okay, it makes your math easier because then you're not having to subtract out what you already accounted for. Okay, so it's like starting back over from the beginning. All right, again, we know that we have 0.0084 moles of HOCl. In order to completely neutralize the HOCl, how many moles of OH minus do I need? The exact same as the HOCl. Because remember, at the equivalence point, moles of HOCl equals moles of OH minus. The moles of the acid equal moles of the base. So therefore, this has to be the same. So since that's the same, we know the concentration of the hydroxide. We know the moles of the hydroxide. We can find the volume. Okay? And that should be 42 milliliters. But you can check it just to make sure. Yeah, you should get 42 milliliters, or 0.042 liters. So on our graph, this point would be 42 milliliters. Again, not to scale. Okay? What about the pH at the equivalence point? What is the pH at the equivalence point? So remember, we had this reaction We know that these are equal. Right? Since these are equal, there's a complete neutralization. So both of these are going to be used up. And we're going to make that same amount of the conjugate base. And remember, what scenario is this? Three. Scenario 3, where all we have left at the neutralization point is, because remember, don't forget, an acid plus a base forms water and a salt. If you have equal amounts of your acid and base, all that's left is salt and water. So OCl minus is our salt. It's just we don't care about the cation of it because it's a spectator. And this goes through hydrolysis. That's why it's scenario 3. Okay? So we have to do two things. We're going to have to put this in a rice table, reacting with water. But before we do that, what do we need to do with these moles? Convert it back to concentration. So we're going to divide it by the total volume in my beaker at this point. Okay? What was the volume of HOCl I put at the very beginning? 24 milliliters. And at this point, what volume of NaOH has been added? 42. So what's my total volume? 66 milliliters, or 0.066 liters. So go ahead and find that concentration, and that's what we're going to put in our rice table. Did you get like 0.127? I'm not worrying about sig figs right now, because again, all I care about is sig figs on my final answer. I know I should only have 2 sig figs, but I'm going to report a little bit more for right now. I'm going to carry a few more and then round off for sig figs at the end. Right? Okay. So I'm going to put OCl minus in a rice table. The reason scenario 3 is such a pain in the butt is because you have to do like KB, like kind of work backwards. But it's a really special and important circumstance of our titration. So we put our ion in water, and it goes through a Bronsted-Lowry reaction. What are my products here? OH minus and HOCl. Just like always, I don't care about the amount of water. My initial concentration for OCl minus is the 0.127. After the neutralization is complete, up here in what I did in purple, all I have left over is the OCl minus, and then that comes back to equilibrium. But initially I have none of the OH minus and the HOCl. But some of it's going to be reproduced as OCl comes back to equilibrium in water. Okay, that's where it comes from. Okay? All right, so what are my changes? Minus x, plus x, plus x, x, 0.127 minus x. All right, I'm going to write what expression of this? A what? A KB. Why am I writing KB and not KA? Because of the OH. So it's going to be KB equals the concentration of OH minus times the concentration of HOCl all over the concentration of OCl minus. But wait, I don't know KB. But I can calculate it exactly. Because I know Ka. Because remember, Ka times Kb equals Kw. Kw is 1.0 times 10 to the negative 14. Ka was given at the beginning of the problem. 3.5 times 10 to the negative 8. So I divide them to get my Kb. And you should get 2. We'll do 2.9 times 10 to the negative 7. Right? Almost done with letter G, and then we'll do H, and then we'll be done. Okay? Power through. I know your brains probably feel like mush. Let's just really mash them the rest of the way, right? All right, so 2.9 times 10 to the negative 7 equals x squared over 0.127. Can this minus x be negligible? Yeah. 0.127 divided by that kb, that's a huge number. X is so small in comparison to that initial concentration of OCl minus. Okay. So we can go ahead and solve for x. Which will be the concentration of OH minus, which will then allow me to get to pH. And that's, I got 1.9 times 10 to the negative 4. Is that what you guys got? So negative log of that will give me POH, and then 14 minus that will get me pH. What do you get? 10.28. That's like actually a pretty high pH. But wait, shouldn't the equivalence point be 7? Nope, only for strong acid, strong base titrations. Whenever you have a weak substance, the pH is not, at the neutralization point, isn't exactly going to be 7. Kind of like with salts, basic salts are going to have a pH greater than 7, acidic salts are going to be less than 7, and neutral salts will be exactly 7. So similar type concept here. So back to our graph. At that endpoint, we know that we needed 42 milliliters. Oh, this is like off. I'm off center a little bit, I just realized. So what happens when I do this wall off to the side. This was 42 milliliters. Okay, so this has a pH of 10.28. Okay. All right, and spoiler alert, all titrations of weak acids and strong bases will have a pH greater than 7. And as we add more and more of this base, the pH is going to continue to rise. It's going to get higher and higher. Okay. Well, let's talk about, like, what if we added just 5 milliliters past that neutralization point? Just 5 milliliters. We hit that equivalence point, and we're just going to add 5 more milliliters of the sodium hydroxide. What will the pH be? No, sorry. Let's calculate it. Okay, that was a rhetorical question. All right, so so our reaction is OH minus plus HOCl going to OCl minus plus H2O. Like always, we don't care about the amount of water. All right, so none of the OCl minus to begin with, because again, we always consider these problems to be like complete problems in and of themselves. Okay, it's just easier that way. We had 0.0084 moles of the HOCl. At this point, what volume of OH minus has been added? 47. So instead of, because it's 5 milliliters plus the 42 from the equivalence point. So 47 milliliters total. So if I have 47 milliliters of a 0.2 molar solution, what is that how many moles is that? 0.0094. So now who is my limiting reactant? Yep, our weak acid. We have less of the weak acid. We've added so much of the sodium hydroxide that it's used up all of the weak acid, and we're exceeding that buffering capacity. So now we're going to subtract out the amount of our weak acid from everything on the left, add that to the right. How many moles of OH minus are left over? 0.001 moles. Okay. What scenario is that? Scenario 1. Okay, because we have something that's strong still left over. The strong won out. The invasion was successful from the strong point of view. Doesn't even matter that we have some of this conjugate base left over, because the strong base, the OH minus that's present in the solution, takes over. It takes the precedent. Okay, the amount of this is negligible. The amount that this affects the pH is so, minuscule. Okay. So now it's scenario 1. We just need to find the concentration of hydroxide left in solution and do negative log of that and then 14 minus that. Okay. So in order to find the concentration, I need to divide the moles by what? By my total volume, which is the 47 of NaOH I've added plus the 24 of the HOCl I had in solution to begin with. So 71 milliliters or 0.071 liters. So what is that concentration? And technically we need 2 sig figs because there should have been a 0 after the 1 in our moles. What do you get? 0.014 molar. So negative log of that, and then 14 minus that will give us our pH. What do you get? 12.15. Okay. Let me go back to the graph I was drawing over here. So, my axis is not big enough. But if we continued adding more of the sodium hydroxide, you'd actually find that the pH would not have as much of an increase anymore. Okay, it would just kind of taper back off. Not going to be that sharp rise around that endpoint like we had. Okay. I'm going to go back to this page for a little bit. Were you guys done here? I'm going to stop the video there.